On October 13, 2025, the world of high-performance computing received a jolt. Researchers at Peking University published a paper in Nature Electronics describing a new kind of chip. Not an incremental digital upgrade, an analog computer chip claiming to run critical AI tasks with breathtaking efficiency. Headline numbers: throughput up to 1000x versus top Nvidia GPU's energy efficiency gains a 100x or more. In an industry of fierce competition and geopolitical tension, these numbers are more than technical. They could be a paradigm shift. It could reshape AI and the global semiconductor map. This comes at a critical juncture. GPUs powered the AI revolution, creating insatiable demand for compute. Nvidia built empires meeting that demand. That created a virtuous cycle of powerful hardware, proprietary software ecosystems. To understand the significance of this breakthrough, one must first appreciate why analog computing was largely abandoned decades ago. In the mid-20th century, analog computers were common. They represented numbers using continuous physical quantities, such as voltage and current. They performed calculations by manipulating these signals with circuits. Imagine a calculator where the number 5 is represented by exactly 5 volts. This approach was incredibly fast and energy efficient for certain problems, like solving differential equations. The physics of the circuit did the math instantaneously. However, this elegance came with a fatal flaw: noise. Electrical signals are susceptible to temperature fluctuations. They are affected by manufacturing imperfections. They pick up electromagnetic interference. This lack of precision became the Achilles heel of analog systems. In an analog circuit, a signal meant to be 5 volts might drift to 5.01 volts, or it might drift to 4.99 volts. But as calculations became more complex, these tiny errors accumulate and compound. They quickly render the final result useless. The digital revolution offered a solution. It represents information as discrete binary digits, ones and zeros. A 1 is a 1 and a 0 is a 0. The Peking University chip achieves its remarkable performance through a clever fusion of novel materials and a hybrid computing architecture. At its heart is a component called a resistive random access memory, or RRAM. Unlike traditional memory that stores data as an electrical charge, RRAM stores information by changing the physical resistance of a material. Think of it as a microscopic, programmable resistor. By applying specific voltages, you can set its resistance high or low, representing a 0 or a 1. RRAM can also hold a wide range of intermediate resistance values, making it ideal for analog computation where numbers are continuous. The researchers arranged these RRAM cells into a dense grid called a crossbar array. That structure enables in-memory computing. In a traditional von Neumann architecture used by CPUs and GPUs, data is constantly shuttled between memory and processors. That movement is the von Neumann bottleneck, costing time and energy. The RRAM crossbar eliminates this. Data, the resistance values, is stored where the computation happens. Apply voltages to the rows, read currents from the columns, and the chip performs matrix vector multiplication, a core AI operation. It does this directly through physics, Ohm's law, Kirchhoff's law. The real innovation is how they solved precision. They built a hybrid scheme combining analog and digital. The claims made in the Nature Electronics paper are defined by a few key numbers. The first and most eye-catching figure is up to 1,000 times throughput improvement compared to high-end digital processors. This claim was based on tests solving matrix equations, specifically a task known as large-scale MIMO signal detection, which is crucial for 6G wireless communications and shares mathematical properties with AI workloads. When comparing performance on a 128 by 128 matrix problem, the analog chip demonstrated a massive advantage. To put this in perspective, a task that might take a powerful GPU over 15 minutes could theoretically be completed in a single second on the analog chip. The second critical number is the 100 times improvement in energy efficiency. Some reports have even cited energy gains as high as 1,000 times. the operational cost of AI is increasingly dominated by electricity consumption and the associated cooling infrastructure required for massive data centers. A 100-fold reduction in power usage would translate directly into enormous cost savings for cloud providers and make large-scale AI more environmentally sustainable. The third, and perhaps most technically significant number, is the 24-bit fixed-point precision. While not identical to the 32-bit floating-point standard common in scientific computing, 24-bit fixed-point is more than sufficient for a wide range of AI inference, and even some training tasks where models have been shown to be surprisingly resilient to lower precision arithmetic. The Peking University chip is significant not just because it is fast, but because it represents a fundamentally different architectural philosophy. The dominant paradigm in computing for the last 70 years has been the von Neumann architecture, where processing and memory are separate physical units. Data must constantly be moved between them over a bus, creating a traffic jam that limits speed and wastes energy. GPUs mitigate this by using very wide buses and highly parallel processing cores, but they still operate within this fundamental framework. This new analog chip, by contrast, embodies the principle of in-memory computing. The RRAM cells that store the data, as levels of resistance, are the same components that perform the calculation. When input voltages are applied, the physics of the circuit network solves a complex mathematical problem almost instantaneously. There is no fetch-execute cycle, no shuttling of data packets back and forth. It is as if the data, computes itself. This architectural shift is the primary source of the chip's claimed speed and energy efficiency advantages. The strategic implications of this breakthrough cannot be overstated, especially in the context of the ongoing chip war between the United States and China. For years, the U.S. has used its dominance in semiconductor design and manufacturing technology as a tool of foreign policy, imposing strict export controls on high-end chips like Nvidia's 100 GPUs. 120 GPUs. The goal has been to slow China's progress in artificial intelligence and other strategic sectors. These restrictions forced Chinese tech giants to rely on less powerful alternatives and to invest billions in domestic replacements. A slow, arduous process. The Peking University chip changes the calculus. It shows a viable path for China to build world-class AI accelerators without the most advanced Western fabs. The prototype was built on a commercial 40-nanometer process node, a node widely available in Chinese foundries, and outside the strictest export controls, which focus on 14 nanometers and below. While the performance claims of the analog chip are impressive, dethroning Nvidia is a far more complex challenge than simply building faster hardware. Nvidia's most formidable defense is not its silicon, but its software ecosystem, CUDA. For over 15 years, Nvidia has cultivated a vast and deeply entrenched software stack that makes its GPUs accessible and powerful for developers. CUDA includes libraries, compilers, APIs. These have become the de facto standard for AI research and deployment. Millions of developers are trained on it. TensorFlow, PyTorch. This software moat presents an enormous barrier to entry for any competitor. A new chip, no matter how powerful, is useless without software that can effectively program it. The Peking University chip, with its hybrid analog-digital architecture, would require an entirely new software toolchain. A groundbreaking paper in Nature Electronics is a starting point, not a finish line. The journey from a successful laboratory prototype to a commercially viable, mass-produced product is notoriously long and fraught with peril. While the chip was made on a mature 40-nanometer process, ensuring the uniformity and reliability of RRAM devices across a large wafer is a major challenge. The analog nature of the device makes it highly sensitive to tiny variations in the manufacturing process. What works for a small test chip might not hold up when producing millions of units with acceptable yield and consistent performance. Another significant challenge is the stability and endurance of the RRAM cells themselves. Resistive memory can suffer from issues like resistance drift, where the stored analog value changes slightly over time, or wear out after a certain number of programming cycles. Extensive testing and materials engineering will be required to prove that these devices can maintain their precision, over billions of operations and a lifespan of several years, as expected in a data center environment. Beyond the hardware itself is the challenge of system integration. This new analog chip cannot exist in a vacuum. It must be integrated into existing digital computing infrastructure. This will require developing new chip-to-chip interconnects, designing motherboards that can host these hybrid systems, and creating software frameworks that can manage the flow of data between the analog accelerator and the host CPU. Looking ahead, the emergence of this high-precision analog chip opens up several possible scenarios for the future of AI hardware. The most likely near-term outcome is not a complete disruption of the GPU market, but rather a future of coexistence. In this scenario, analog accelerators based on the Peking University design will be developed as specialized coprocessors. They would be deployed in data centers alongside CPUs and GPUs, tasked with offloading the specific massively parallel matrix computations where they excel. A workload manager would intelligently route tasks, sending linear algebra to the analog chip, and more general or irregular tasks to the GPU, creating a more efficient heterogeneous computing system. A second, more ambitious scenario involves the analog chip finding a dominant niche at the network edge. The claimed energy efficiency is the key enabler here. The bottom line for today, October 23, 2025, is this. The Peking University analog chip is a scientifically significant and strategically important breakthrough. The core claims are real and have been published in a top-tier peer-reviewed journal. 24-bit precision, up to 1,000-fold higher throughput on specific tasks, around 100-fold better energy efficiency. These numbers come from tests on a chip built with a mature 40-nanometer process, and they directly challenge the assumption that high-performance AI computing is exclusively the domain of cutting-edge digital processors. This development requires urgent attention from technologists, investors, policymakers. However, urgent does not mean immediate. What do you think? Is Nvidia facing its biggest challenger yet? Or is this just another breakthrough that will take years to matter? Drop your thoughts in the comments, and if you enjoyed this breakdown, smash that like button and subscribe for more tech analysis. Thanks for watching.